the puck demo analysis. We have that really cool air puck that we saw in class. And for each of these situations, you can either imagine and or watch the videos that are also posted and a playlist with this assignment. Please make sure that you've read all of the directions so you know how to do all the parts, but we're just going to pick things up and run with it from here. The first problem says the puck, which is at rest, is on a level floor and experiences no horizontal forces. First thing you want to do is define the system as the puck. And again, it's sitting at rest on the floor. So if it's at rest, what's its velocity? Its velocity would be 0, and therefore its acceleration would be 0 as well. So let's say what forces are acting on this puck. Well, if it's at rest on the floor, what's pulling down on the object?
Gravity.
Gravity, great. So there's a force of gravity acting on the puck by the earth. We always want to say it that way. Force of gravity on the puck by the earth. And since it's remaining at rest, it's not accelerating up or down. What else is pushing up on it? We've got a surface of some sort. But what's really unusual, this is a hover puck. So it's got a fan on the bottom of it so it can move frictionlessly. So instead of it just sitting on the floor or on a table, it's actually hovering on a layer of air. Now, it's going to be a normal force, kind of like it was at rest on the floor. And there might be some teachers that would say this would be like a force of lift. But we're going to just say force normal on the puck by the air. It's floating on a layer of air. And if this upward normal force is exactly the same size as this downward negative force, when we added these two together, the sum of those forces would be 0. So the net force, or sum of the forces, would be 0. And again, we talked about this in class already, but sigma F means net force. The sigma is a Greek letter for the letter S. And just like we use D for delta, which means the difference, this means the sum of the forces. So we have to add them up. So this big of an upward force plus this big of a negative force, the sum of those two things would be 0. Student in the hallway, you can come in and be silent and hang out with us. What will this puck do if it's at rest and it's experiencing no net force? It will
Remain at rest.
And back again, we learned how to do motion maps. If an object's at rest, at some time it's going to be at a position, and sometime later it's still at that same position. So we just stack the dots, and these should be stacked vertically. No velocity vectors, no acceleration vectors for problem number 1. So that was an object sitting at rest on a floor with no horizontal forces. And let's move on to number 2. So in this case, the puck is moving moving to the right on a level floor, but experiencing no horizontal forces. Now recall, this was a hover puck. So it moved across the floor, and because it wasn't touching the floor, there was no friction. So what kind of motion did we see? It moved at a constant velocity. The puck will move at a constant velocity. And in this worksheet, we need to include both the type of motion, constant velocity, as well as direction. And we said it was moving to the right. Constant velocity to the right. Awesome. And what forces are acting on it? This would have been after it left my hand, but before the other person caught it. Was there still gravity pulling down on the object?
Yes.
Force of gravity on the puck by the earth. And what was pushing up on the puck? It was on the surface, right? Or actually sitting on that layer of air acting like a surface. So again, we have force normal on the puck on that layer of air. And let's remember those forces are vector quantities, so we need to include that. Are there any horizontal forces? And it says no horizontal forces. So if there's only this upward normal force that's positive and the exact same downward negative force, if we add those two together, the net force would be
0.
0. And what would our motion map look like if an object was moving to the right at a constant velocity? Well, would our position dots would they be equally far apart, or getting further apart, or getting closer together? And they would be equally spread out. So I'm going to use the hash marks, and I'm going to make my position dots every 2 hash marks, and I'll make my velocity vectors maybe 1.5 hash marks long. And I'll remember to mark my velocity vectors with a single little hash to say, hey, those are all the same size. Trick question, do any of these get acceleration vectors? Well, is the velocity changing? Is the velocity changing? Nope, it's a constant velocity, so the acceleration has to be 0. There's no change in velocity, so there's no acceleration, and there's no acceleration vectors. So that's 2 problems in a row that the net force was 0 and the acceleration was 0. We'll have to keep an eye on that moving forward. Let's take a look at let's pause at this point, and then we'll start a new videos for 3 and 4 and 6.